this video, we're going to learn how to set up and program a thermistor. Thermistors are perfect for any project that needs to measure temperature or control things based on temperature. We'll output temperature readings to the serial monitor, then make a temperature switch that controls an LED.
This is what a thermistor looks like. It's pretty small, and it kind of looks like a tantalum capacitor. There are two leads, but thermistors are non-polarized, so there isn't a positive or negative lead. They can be connected either way around. Thermistors are variable resistors that change their resistance when the temperature changes. They're specified with a resistance value called the R25 value. The R25 value is the resistance of the thermistor at 25 degrees Celsius. This is a 10 kiloohm thermistor, so its resistance at 25 degrees Celsius is 10 kiloohms. Thermistors are also specified by their temperature coefficient. The temperature coefficient can be either positive or negative. In positive temperature coefficient thermistors, the resistance increases with increasing temperature. In negative temperature coefficient thermistors, the resistance decreases with increasing temperature. Most thermistors used for Arduino projects are negative temperature coefficient thermistors, so that's what I'll be discussing here. Since thermistors are variable resistors, we can use a voltage divider circuit to measure the voltage drop across the thermistor as the temperature changes. Once we know the voltage drop across the thermistor, we can use the voltage divider equation to calculate the resistance of the thermistor at each temperature. Here's how that will look when it's wired up to the Arduino. Here's the thermistor, and here's the resistor. One tricky thing about this circuit, though, is that you have to be sure that the resistor here is the same resistance as the R25 value of your thermistor. For example, if you have a 10 kiloohm thermistor, this resistor needs to be 10 kiloohms. If you have a 100 kiloohm thermistor, the resistor needs to be 100 kiloohms as well. The middle of the voltage divider is connected to analog pin A0 on the Arduino. The other lead of the thermistor is connected to 5 volts, and the other side of the resistor is connected to ground. Before we jump into the sketch, we need a little background information about how a thermistor's resistance is related to temperature. Unfortunately, it's not a simple linear relationship. It's logarithmic. The precise relationship is best modeled by a formula called the Steinhart-Hart equation. The Steinhart-Hart equation describes the temperature-resistance relationship with about 0.02% accuracy. The equation looks like this. The formula solves for the inverse of temperature, but we can rearrange it to solve for temperature. R is the resistance of the thermistor at a particular temperature T. A, B, and C are constants that depend on the resistance, tolerance, and construction of the thermistor. The math to calculate the constants is pretty advanced, but luckily there are online calculators that will do it for you. The thermistor I'm going to use for this video is an MF52103 10 kiloohm NTC thermistor with a plus or minus 1% tolerance. If you're using the same type of thermistor that I am, you can use the constant values I'm using. But if yours is different, I'm going to show you how to calculate them. I found a good online calculator for the Steinhart-Hart coefficients. All you need to do is input the resistance of the thermistor at 3 different temperatures. If you don't have a datasheet for your thermistor, you can use a multimeter to measure its resistance at 3 different temperatures. But I have the datasheet for my thermistor, and it has a table of the resistances for a range of temperatures. You just need to know the beta value and the R25 value. The beta value is something you need to get from the manufacturer. The thermistor I'm using has an R25 value of 10 kiloohms and a beta value of 3,435. So let me scroll down here and find the resistance table. Here it is. The first column shows the temperature, and the second column shows the resistance at that temperature. It's best to use the lowest, highest, and middle temperatures the thermistor is rated for. For example, if your thermistor is rated from -40 to 105 degrees Celsius, you would use the resistances at -40, 25, and 105 degrees. The resistance of my thermistor at -40 degrees Celsius is 190,953 ohms. I'm going to input that into the calculator. At 25 degrees Celsius, the resistance is 10,000 ohms. So I'm going to input that in the calculator too. It's actually already set at 25 degrees and 10 kiloohms. The resistance of my thermistor is 858.33 ohms at 105 degrees Celsius. So I'll input that too. To run the calculator, press the Enter key. Now if you look at the graph over here, this is plotting resistance on the y-axis and temperature on the x-axis. The curve is logarithmic. Over here are the calculated Steinhart-Hart coefficients, A, B, and C. So now let's look at the sketch, and we'll come back for these numbers later. The center of the voltage divider is connected to Arduino pin A0. So I have an int variable called thermistor pin to store that pin number. Then we need a variable to store the value of the resistor in the voltage divider. Let's store it in a float variable called R1. I'm using a 10 kiloohm thermistor, so my R1 is 10,000 ohms. If you're using a 100 kiloohm thermistor, your R1 would be 100 kiloohms. Now we declare some float variables for the calculations we're going to do. R2 will hold the resistance of the thermistor after we calculate it with the voltage divider formula. Then we have log R2, which holds the natural log of R2. Log R2 cubed holds the natural log of R2 raised to the third power. Tk will hold the current temperature in kelvins. Tc will hold the current temperature in Celsius. And Tf, which will hold the current temperature in Fahrenheit. Then we define the values of the Steinhart-Hart coefficients and store them in float variables A, B, and C. These numbers are taken from the Steinhart-Hart calculator I showed you earlier. Here's the A coefficient. So that goes here. Here's the B value. That goes here. Here's the C value. and that goes here. Now down in the setup section, we just need to initialize the serial monitor. In the loop section, we take an analog read of the thermistor pin and store the result in a local int variable called vout. Remember that analog read returns a value between 0 and 1023. 0 corresponds to 0 volts, and 1023 corresponds to 5 volts. This corresponds to the voltage drop across the thermistor. So now we can convert that to the resistance of the thermistor. So we use the voltage divider equation, which has been rearranged to solve for R2 instead of vout. We have R2 equals R1 times 1023 divided by vout minus 1. R2 is the resistance of the thermistor, and R1 is the other resistor in the voltage divider. 1023 is the input voltage of the voltage divider, which is 5 volts. And vout is the voltage drop across the thermistor. The Steinhart-Hart equation uses the natural log of R2. To get the natural log of R2, we can use the log function with the name of the variable as the argument. We store the result in the global float variable log R2. Then we have to calculate the natural log of R2, raised to the third power. To do that, we can use the POW function. The POW function takes two parameters. The first parameter is the base, and the second parameter is the exponent. Since we want to raise log R2 to the third power, we have log R2 as the first argument, and 3 as the second argument. This is stored in the log R2 cubed variable. Here's where we do the Steinhart-Hart equation math. The Steinhart-Hart equation gives the temperature of the thermistor in degrees Kelvin. So we store the result in the variable Tk. The equation is 1 divided by the A coefficient plus the B coefficient times the natural log of R2 plus the C coefficient times the natural log of R2 raised to the third power. So this will give us the temperature of the thermistor in kelvins. But kelvins aren't very useful unless you're building a sensor for a physics or chemistry project. So let's convert kelvins to degrees Celsius. To do that, we just subtract 273.15 from the temperature in kelvins. The result will be stored in the TC variable. Let's go a step further and convert the temperature in Celsius to a temperature in Fahrenheit. To do that, we just multiply the temperature in Celsius by 9, then divide by 5, and add 32. The result is stored in the TF variable. Now we just need to print the values to the serial monitor. Here I'm printing the word temperature equals, then the TC variable, which holds the temperature in Celsius. Just replace this with TK or TKF if you want the temperature in kelvins or Fahrenheit. Then I use serial print line to print a letter C to show that the temperature is in Celsius. Lastly, I added a delay of 500 milliseconds to slow the output down a bit. Okay, so let's see what this looks like. So here's my thermistor. I have a glass thermometer here as a reference. The temperature from the thermistor is reading about 26 degrees Celsius. If you look at the glass thermometer, you can see it's reading 27. So that's pretty close to the reading from the thermistor. When I hold the thermistor, you can see the temperature go up. And it comes back down to the ambient temperature when I let go. Alright, so this is great if all you need to do is measure temperature. But thermistors can also be used to control other devices. For example, you could place a thermistor near a motor to shut it off when it gets too hot. Or you could monitor the temperature inside of an incubator and turn on a heat lamp when the temperature gets too cold. So now let's see how to control the Arduino's output with the readings from a thermistor. I'm going to demonstrate with an LED, but any device that's controlled by a 5-volt signal can be used here. The thermistor is connected the same way as in the last example. The center of the voltage divider connects to analog pin A0. The other side of the thermistor connects to 5 volts. And the other side of the resistor connects to ground. The LED's anode is connected to digital pin 5 via current limiting resistor. And the LED's cathode is connected to ground. To make the diagram simpler, I have the LED and the resistor in the voltage divider sharing the same ground. Now let's look at the sketch. In this sketch, we're going to make the LED turn off when the temperature passes above a certain threshold. The LED will turn on when the temperature drops back below the threshold. Most of the sketch is the same as before, but now we need a variable to store the LED pin number, which is pin 5. All of these variables for the temperature calculations remain the same. In the setup, we're still going to send the temperature readings to the serial monitor, but we're also going to switch digital pin 5 on and off, so we need to initialize it as an output with the pin mode function. In the loop section, all of this is the same. We take a voltage reading from the thermistor pin, convert it to a resistance, and use the Steinhardt-Hart equation to give us the temperature of the thermistor. Then we convert the temperature in kelvins to Celsius and Fahrenheit. And that gets printed to the serial monitor. Once we have the temperature data to work with, we can use it to control the LED pin. A simple if-else statement is enough to do that. We can use the condition to determine what happens when the temperature rises above a certain temperature. Here, if the temperature in Celsius is greater than 29 degrees, the program will enter this block, where we digital write the LED pin low. Else, in other words if the temperature is not greater than 29, we enter this block and write the LED pin high. So the LED will be on when the temperature is below 29 degrees Celsius, and will be off when the temperature goes above 29 degrees Celsius. Let's check this out. So initially the LED is on. You can see the temperature on the serial monitor is reading about 25 degrees Celsius. When I hold onto the thermistor to warm it up, you can see the temperature increases quickly. And once we pass 29 degrees, the LED turns off. When the thermistor cools down below 29 degrees, the LED turns back on. In the next video, we're going to learn about another way to measure temperature, but this time with the digital humidity and temperature sensor.
The 3-in-1 Smart Car and IoT Learning Kit from SunFounder is a hands-on, all-included electronics kit that is perfect for anyone who wants to learn how to master the Arduino. The kit comes with an Arduino, 22 different sensors and modules, breadboards, jumper wires, and everything else you need to build a bunch of fun and interesting projects. Learn about robotics by building a remote-controlled smart car that can be controlled with an infrared remote controller, or drive on its own and avoid obstacles or fall on a line. Learn about the Internet of Things with a project that lets you monitor the temperature, humidity, and light level of a room from an app on your smartphone. And build a plant monitor that tracks the temperature, humidity, light intensity, and soil moisture, and displays it on your smartphone so you can keep your plants watered remotely. It's a super cool kit, and I had lots of fun building all the projects in it. So click the link in the description below to order the kit from SunFounder.